Let us discuss about the close packing in the solids. What do you mean by this close packing? You know that one of the important property of solid, it says that the solids in the atoms, they are very strong intermolecular force of attraction will be there. So that's why I am going to call that the atoms which are going to be involved in the solids, they are very tightly packed with each other. So, right? So that's why it has a definite shape, definite mass and volume, right? So here, how they will be arranged? We told that they are closely packed with each other, right? So how it will be there? Let us study here. So that is called in one dimension. How the closed packing system will be there in 2 dimension, 3 dimension. Let's see, discuss here. Why? Because in order to occupy the maximum space, and avoid the some vacant space. So let us discuss here. So before going to that, let us study about the coordination number. Why it is important? Let us discuss here. Coordination number is nothing but the number of the nearest neighbors of any constituent particle in a crystal lattice. So once again, it is nothing but the number of the nearest neighbors. Nearest neighbors means if I take this particle, right? These are called as constituent particles. They are arranged in the hard spheres, right? So these, if I going to consider this particle, how it will be arranged? It will be arranged, right? So it is having the nearest neighbors, right? So this will be one nearest and this will be the nearest. Okay. This is the middle portion, right? Left, right. This is the middle. So this middle particle, which is going to be attached with this first one as well as the second one. So that is nothing but the nearest neighbors of any constituent particle in a crystal lattice is going to be called as the coordination number. So without closing us, we can tell that. So this coordination number of this dimension, that is called as the 2. So this is an example for the close packing in one dimension. So let us discuss about the close packing in one dimension. So here in this arrangement of each sphere is nothing but they are very hard spheres. In this arrangement, each sphere is in contact with 2 of its neighbors. That is saying, this sphere which is going to be contact with the 2 neighbor spheres, 2 of its neighbors. So hence its coordination number of the particle is 2, because which particle which is going to be attached with this side and this side, hence this coordination number will be 2. So this is a close packing in one dimension. Because what happens in one dimension? So there is only one way to write the spheres, constituent particles like this, whether it is in a horizontal shape or it is in a row shape. So it is in the row shape. We are going to arrange this constituent particles. This is in close packing in one dimension. This sphere which is going to attach with the 2 neighbors. And also if you take this sphere, if you go to take this sphere, so this sphere which is going to be attached with this side and this side, hence this coordination number will be 2. And also if you consider this sphere which is going to be attached with like this, so like this, which will be happen in one dimension. Let us discuss about the close packing system in 2 dimension. So let us discuss here how the constituent particles which they are going to be arranged in the 2 dimension. So that the 2 dimension is nothing but it is very simple. First you should write the set of the constituent particles in the row manner. So above this row you should place once again another set of the arrangement of the constituent particles like this here. First you should write one row and above this one you should write one more row. So that is called the 2 dimension. So in this close packing system of this 2 dimension, which is mainly going to be classified as this one is called square close packing system. This is called square close packing, and one more hexagonal close packing. So first we should study about the square close packing. So one dimensional close packed sphere are placed exactly one above the other like this. One above the other and one below this row, right? So and these spheres are arranged horizontally and vertically. So when you look at these spheres, so how they are arranged? They are arranged horizontally like this. They are going to be arranged in a horizontally as well as the vertical like this. This is vertical like this. And each row of one dimension close packed sphere is called A. So just I am going to call this row as A because all are in the similar way, right? So that's why they are going to name it as A set. This is A set of the arrangements. Then square close packing can be recorded as the A. So this is named as the A like this. This is a simple arrangement. And what about the coordination number? Coordination number is nothing but the one sphere. It does the neighboring spheres. We are going to count here, right? So this is one sphere. I am going to take this as the center of this all spheres, this center. So this sphere which is going to be covered up, I mean neighbor with the share with the 4 some other particles, right? So this is 1, second, third, 4. So then what is the coordination number of this close packing system? That coordination number will be 4. Means this sphere which is going to be attached with or packed with 4 other constituent particles. That's why its coordination number will be 4. Let us discuss about the second system of this called hexagonal close packing. So this is also comes under the second dimensions. So let us look at this picture. So these are the arranged like this constituent particles, and this will be the center of this particle which is going to be surrounded by this 6. So that's why its name is called hexagonal close packing system. Let us discuss about the summary of this hexagonal close packing. So it tells that the spheres of the second row placed in the depressions mode, which is going to be created by the first row. First row is called B row and second row is called the A row. So this first and second which is going to be repeated regularly like this. So this is B, this is B. This is third layer, this is first layer. Second layer and fourth layer are be same. So that is depression which is going to be created by the first row here, and this arrangement type we are going to call as the AB type, like this will be there. And when the center of those 6 spheres are connected regular hexagonal, so this is center one of this constant particle which is going to be connected with the 6 other neighbors constant particles. That's why this name is going to be called as the hexagonal close packing system, and hence this particle which is going to be attached with these 6 neighbors of the constant particles, that's why its coordination number will be 6. Let us discuss about the close packing in a 3-dimension system. So this 3-dimension which is going to be mainly formed by the 2-dimension. So when you look at the 2-dimension, that 2-dimension which is going to be formed by the set of the row of the 1-dimension, right? That here also in 3-dimension, set of the 2-dimension rows which is going to be formed together by the 3-dimension. So here in this 3-dimension we are going to form the 2 types, that is called the close packing from the 2-dimension of the square close packing, and also one more is 2-dimension from the hexagonal close packing. So let's discuss about the simplest one, that is called which is going to form by the square close packing system. When you look at this 3D structure, right, this is the 3D structure of the called the square close packing, that which is going to be formed in 2 dimension. So that makes the 3-dimensional picture. This is called close packing in the 3-dimension system. So what it is that arrangement of the 2 dimension. So this is an arrangement. This is called square close packing. How it is formed? By the 2 dimension. That 2-dimension packing which is going to attach with one another above the layer, below the layer. So that is contact with each other. They will be contact with each other. And this packing also leads to the, and you look at this one, that is called the simple cubic lattice form. This leads to the simple cubic lattice. Hence, when you look at this 3D structure, what will be the coordination number? The coordination number will be 6 will be there. So that I have written here, that coordination number will be 6 for this simple cubic lattice of the 3-dimension, which is going to be formed by the 2-dimension of the square close packing system. So in 3-dimensional close packing, so in this case which is going to be formed by the 2-dimensional space of the hexagonal close packing, I mean HCP. HCP is nothing but the hexagonal close packing system. So look at these structures here. Then the set of the 2 layers will be there. So these will be called the dark rows. We are going to call as the A. So this will be called A, and this colored, this row which will be single layer. These spheres which are going to be called as the B layer. So these will be called the first layer. A is called first layer. B is called the second layer here. So here, look at about this. This one is the first layer that we are going to call as the A. So that is called base layer. So here there is a set of the 2-dimensional hexagonal close packing system, that is called HCP. And B is placed on the first layer. This is called B ray. So this will be called B, which will be placed on the first one. How will be there? So these spheres will be in the set of the depressions mode of the triangular voids. So this one term is adjusted here. That is called the voids. Voids is nothing but this empty space. This will be called the voids. This will be called the voids. Voids is nothing but how it will be there. So this will be nothing but the triangular voids. So this is called triangular voids. Voids is nothing but the empty space. So and this arrangement we are going to call as the set of AB arrangement pattern will be there. Yes, and its coordination number will be 12. This coordination number will be 2 because it is a 3-dimension, right? We are not going to count the spheres here. It is not possible also. And example has given the magnesium and zinc. So this is the closed packing in the 3-dimension which is going to be formed by the 2-dimension of the HCP. Let us discuss about the small subtopic is called the voids. Voids is nothing but the empty space. Let us take the definition. That voids can be defined as the empty space or unoccupied space between the spheres in a closed packed structure that we are going to call as the voids or the holes. So first you take this simple one. Void means space between the 3 spheres touching each other that are going to call as the triangular voids. So this name is called the triangular voids. You can see this structure here. Small triangle is going to be formed here, and these 3 spheres which are going to touching with each other, that is forms the void, that is going to call as the trigonal void. Second one, this when you look at this structure here, when triangular void, this triangular void which is going to be covered by the one extra sphere, that may be upper layer or the lower layer, that is going to call as the tetrahedral void. So this name is called the tetrahedral void. And similarly, when the center of the 6 spheres which are going to be joined, then octahedral which is going to be formed, that is called the octahedral void. So this is a simple arrangement showing the pictures. This is called the octahedral void which is going to be formed here. So this is the simple subtopic or the voids.